but she has just the most adorable full face smile. Okay, so should we get started? Um, you all feeling good about the semester so far? Like, I know we're in a big transition. You're also transitioning in the other half of the course too. So yeah, hopefully that feels good. Coming back from break is always, I think, a little challenging, especially when everyone be quiet and look. Welcome. We used to, I was telling folks, we used to, in grad school, we would lock the doors. So it'd be like a whole thing when people walked in. I didn't do that on purpose, I'm sorry. Okay, so let's just remind ourselves what we were doing last time. Essentially, so after we got through the sort of the basic intro stuff, everyone turn and look. Should we clap? Welcome. And it's Lauren, right?
Yes.
Yeah, welcome.
It's so mean because the light's green. And I was like, so I can come in, right? And it's like, no. No.
And is it Garrett?
Yes.
Okay. And Lauren. Okay, so what we started working with last time, I think we got through most of the first topic, numerical derivatives. But essentially, like, the big idea was sometimes we have functions that are complicated in ways that are hard to work with analytically, and we actually want some traction if we don't necessarily need the full analytical derivative, but we just want to know something about the derivatives. So we walked through some of these basic things. So just to get ourselves started with numerical methods, we set up this system of equations, and we thought about trying to solve for x. This was sort of our part 0. Y'all are familiar with doing these kinds of things, so this is like, 2 equations, 2 unknowns. This one's really not that challenging. I mean, I think if you're seeing this for if you haven't done linear algebra in a while, this might take you a minute. But these are things you probably did in high school, or at least the beginning of college, working with systems of equations. So we talked about the solutions here. The way I think about solving this problem, I would multiply the second equation by 2, and then subtract. I'm gonna go. Can you remind me of your name?
Henry.
Henry. Yeah, welcome. I didn't mean to lock the door, but welcome. So the way I would solve this, I would multiply the second equation by 2 and then subtract the second equation from the first equation. And that just gives you the 2 x1s cancel, and then we have 3x2, and we subtract off 2x2 from using the second one, which then gives us, x2 is equal to 6 minus 2, 6 minus 4, and then we get x2 from there. So this is the, a basic setup that we talked about. So this is simple, but sometimes we have complicated ones. So we can actually just, encode this system of equations as a matrix, put that into some code. And this is just a standard method for solving systems of linear equations. So we talked through this, and we can solve it using the linear algebra solver in Python, or we can just use like an inverse and then do matrix multiplication using the standard Python package. And this is really like the way we approach all sorts of things like the general linear model or regression. And you've seen this, I think, in your first sequence. Do you all come in with econometrics from undergrad? You probably have seen a lot of this before. So this probably feels pretty familiar. Like, we're really just trying to minimize the mean squared error. And we do that using an optimization approach behind the scenes, first derivative with respect to the betas and such. And that's fundamentally just a product of matrices. So we multiply our data matrices transposed and inversed in this particular order to give us our betas. So fundamentally, we do a lot of matrix multiplication behind the scenes. And nicely, we have computers to do this. A big part of what we're doing in this course is setting up the skill set for the tools we use in the field. But we're also putting a lot of emphasis on just like understanding what the tools are doing. Today, we're going to build a couple of them from scratch before we kind of offload our thinking to the more standard packages. So we're actually going to walk through a sequence building up optimization tools in the second half of class today. And then we're just going to use the standard packages after we do that. So we talked about numerical derivatives. This was the first numerical method. So the idea is sometimes we have tools that we, or functions that we care about, but we don't necessarily care so much about all of the analytical solution. Sometimes we just want to find derivatives at particular points. We don't need to know the functional form. We just need to know like how we get the slopes and such. So we have a couple of functions we were talking about last time, which we're going to return to today. The first one is pretty straightforward. I think all Calc 1 students can solve this. Basically just power rule. Second one is a little more complicated. We have the product rule plus the power rule. And then this one, I think, frankly, I would struggle to solve it on my own. Like this is, I have the solution here, but this is just a really challenging problem. This is going to get, I think, is someone trying to get in? I'm going to ignore that door. If someone's trying to get in, you all just maybe help them out. I'll ignore the door after 9:05, but it's funny before then. Okay. And you can be late to class. Like I don't really mind that much. I'm just making a big fuss of it because it's like day 2. So for the way we set up our sort of solution concept is we want to, the actual like analytical derivative you're familiar with. We essentially find a small change in x. We plug in those two very close values into the function, and then find the difference in the functional evaluations. And then we find that ratio. That gives us our, the delta y over the delta x. When we construct calculus, like calculus relies on taking the limit as that difference gets smaller and smaller. But we can approximate the analytical derivative using very small changes. That's the entire approach for numerical derivatives. And we're going to rely on this really throughout the semester. So what we can do is just define a function. This is what we did last class. So I had the numerical derivative, which is just evaluating, it's doing exactly this. So I'm evaluating the function at x plus some epsilon, which is going to be very, very tiny. And then I'm going to evaluate it at x. So we have the difference in these two evaluations. And then we divide that by the difference in the x. So this is the epsilon itself. In calculus, we take the limit as this thing gets smaller and smaller. But here we're just going to approximate it using a very small number. So last class we walked through this easy example. So this was, one we have the function and we know exactly what the functional form looks like. So I defined easy f as the easiest function, which looked like this. And then I defined the derivative as well. And then what we did is we just took the numerical derivative. So we defined some very small increment. And you'll remember this is 1 times 10 to the negative 7 power. So this is like 0 point, then 7 zeros, and then 1. And then we did the numerical derivative, and we did the easy function analytical derivative. And what we found is the numerical derivative was really close. You can see this is not exactly the same as the analytical derivative because we're dealing with incredibly small increments, but that are not 0. And we found the difference. And in general, this is not like a hard and fast rule, but the error in our estimate, our approximation, is going to be generally in the order of magnitude as the epsilon. So you can sort of, if you need to be more precise, you can make the epsilon even smaller. Okay, and then our second example was this one. So we basically just multiplied this e to the negative x over 10 times our original function. I coded that up here using the original function, so we're just multiplying the exponent or exponential of negative x over 10. And then we had the analytical derivative as well. So here I did the same thing. So had a small increment, numerical derivative, analytical derivative, and then find the error. And here again, it's more complicated, but we get the same result, right? So we the approximation is pretty close to the analytical solution. And so just to give us a sense of what we're doing here, I plotted a little figure. We're not going to spend a lot of time in this class talking about data visualization, but this is just a little function figure showing what the function looks like on this range. And we're going to actually spend a lot of time with this function today, for better or for worse. So this is another, this is just plotting out so this is the function of a graph of the function itself. And then this is a figure of the numerical and analytical derivatives. So we know exactly what the analytical derivatives look like because we had just computed them. So we can just make a plot of all of the analytical derivatives using the derivative as the function. And then I'm just going to plot the numerical solutions across much of our domain. So I did this first for the numerical derivatives. So I'm just running a for loop and constructing the numerical derivative at a bunch of x's in our x range from 0 to 101. And then I'm just plotting the results, both for the analytical solution and for the numerical solution. And the point of this is to show you not only can we find particular values, but this approach also gives us the flexibility to do lots of sort of small increments. So we can get functions or like figures of functions, even though we're not actually doing the estimation of the functional form itself. So we can just plot the evaluated derivatives across the domain. Okay, and then what we wanted to do was check how close each one of these values was to the analytical. So we made a bunch of approximations, and we wanted to see if there's any systematic error. It turned out that there was, and this is to do with the forward and backward definition of the derivative that we're measuring. So because we're measuring, it's like f of x plus the epsilon, and then we subtract off f of x. It's in one direction. So this sort of introduces if you can think of the mistake is only on one side, where if we take sort of mistakes on both sides. So if the approximation goes in both directions, we might be able to do better. So this was our first approach. You can look at the scale of this thing. Like, I'm plotting this in deeply zoomed in detail. The vertical axis, the error is like 0.000005. So these are not meaningful errors, but we can still do a little bit better. So we walked through thinking about, so we talked through higher order derivatives, which are really just applying the same approach. We walked through some of this math here, which ended up giving us, this is the definition for the second derivative in epsilon terms. So very similar to the second derivative using limits. But here again, we're using an approximation, which is just, so we have epsilon in one direction and then evaluated at x in the other direction. So we're basically just swapping out the derivative for the function in the epsilon definition. But we know exactly what f prime is when we're approximating it. So that's once we plug all that in, we get this thing. So this is just, we're not going to spend a lot of time with the math again, but this is the definition for the epsilon second derivative, which looks like this. So I just coded it up here. So if we wanted the second derivative, we just really applied that same approach. So not a lot of new ideas here. The main idea with this approximating the second derivative is that we have an approximation for the derivative of any function, which we can then just plug in our definition for the first derivative into the definition for the second derivative, and that gives us the approximation approach for the second derivative. Okay, we were talking about trying to be accurate. This is the Taylor series, very nicely named. You're probably all familiar with this. We talked through this last time. We can just rearrange this essentially to give this thing. And what we found with the single direction epsilon is that we have an approximation for f prime with some error term that's a function of epsilon. But it turned out if we look at both directions, so we talked through some of this math in two directions. So we're setting up the Taylor series expansion in both directions, both the positive and the negative direction for epsilon. And we combine these things, we get an approximation for the first derivative with an error term that's a function of epsilon squared. So this is like, we took the error term, but now it's converging twice as quickly. So epsilon to the second power. So this is just, this is what we call the centered derivative or two-sided derivative, or second difference, centered difference equation. This just gives us, in theory, a better approximation of the derivative. So I set this up, functionally I called this the better derivative, but you can call it whatever you like. And I just plotted a figure of the two errors, one with a forward difference and then one with a centered difference. And you can see this one is just much, much better. So if we really, really care about how wrong our model is, if we need to be very close to the analytical solution, the centered difference approach just works better. And you can take this much further. Like, there are ways of using the Taylor expansion to get us even closer. But in general, like, this is going to be more than enough to find the derivatives. Okay, and I think this is where we left off last class. Any questions here? frankly, it's amazing that we have computers to be able to do this, right? Like sometimes this happens to me a lot of the time. I sit down with a new solution. Like I care about the analytical solution most of the time, and usually I'm trying to get to the analytical solution. But sometimes if I'm just wanting like a figure, or I want just some insight about the problem, approximating it is just more than enough. So in practice, this is just a really powerful tool to use. Okay, so that's all the first part of what we're doing in numerical methods. The second part is thinking through numerical solutions to equations. And we're going to spend a lot of our time thinking about finding roots. So, if we have linear equations, these are very well defined. Is it fine if we just go through the notebook? Does this bother you? I don't usually present just directly from a notebook, but I think for this class, I think this is the right way to go instead of slides. I think it feels more interactive in a certain kind of way. If you don't like it, just let me know, and we can maybe make slides. All right. So so linear equations. We talked about how we can turn linear equations and systems of equations into matrix form, and then solve those using linear algebra solvers. Those are very simple to solve. But with nonlinear equations, this is more tricky. So this is a nonlinear equation. X to the fourth is equal to 12. And we can solve this just by inverting the function. So it's nonlinear, but we can solve it because it's invertible. So we just raise both sides to the 1/4 power. But not every nonlinear function can be invertible or is easy to invert. You'll run into this a lot when working with your own equations, but this is not a radically complicated one, but this is not easy to invert. And then sometimes we have equations that look like this that have multiple solutions. So this is also not very complicated, but the solution to this thing is the quadratic equation, which has a plus or minus, which I don't like. That's not fun. Gives us multiple solutions. We'd wish for better, but this is what the math is telling us. So even with relatively simple equations, we can go down these complicated rabbit holes. Not to say that this is particularly complicated, but it would be nicer if there was a unique solution. We have a plus or minus because there are two possibilities. Okay, so we just want a simple way to solve these things. We want, just a general approach that will do a lot of work for us. And the rabbit hole we're going to go down today, I'm going to show you first off a general solution, like the simplest one, the workhorse model for how we've solved these kinds of equations. And then if we have time, I hope to make it all the way to the end. I'm going to show you some other approaches that we use that are very different than this. But this is the one we use most of the time. And this is the one I recommend you use for nearly all your problems. I guess not all your problems. Some of your problems are personal and don't involve numerical solutions. Unless you're a true economist, and then all your problems are numerical. That's not true. So the general approach here is if we find the derivative, we know something about the slope, and we can essentially do like slope following, like a gradient descent approach, which actually like all of like deep learning that we use in AI, this is all gradient descent. So we use these kind of like hill climbing algorithms really in every area of optimization. The reason we don't use it for these kinds of things with linear models is we actually don't need to. We actually just have a closed form solution that allows us to just write down matrix multiplication to give us an optimization solution. But that's not always going to be the case. We'll come back to this later in the semester, but sometimes we have a link function, which means our linear model is not linear. And in those cases, we actually don't have a nice closed form solution like this. So we actually have to, behind the scenes, we're doing gradient descent to approximate the solution to our model fitting. And all of that relies on this kind of approach, where we basically do hill climbing. Okay, so let me just talk you through the details of what this tells us. The general solution idea is what's called Newton-Raphson. And I'm going to give you both the mathematics and the intuition for how this works. And then we're going to code it up and run a few little examples. Okay, so the first thing is we just need to pick a guess. So we're going to start with a guess. If you have a figure if you plot the graph, in this case, we're going to start with one dimension, which means, with a computer, we can just take the function, code it up, and then plot a figure of the thing, which is going to give us a really good sense of the general region for where the solution will be. And when we talk about solutions here at the beginning, we're going to talk about roots. So we're trying to find where the function is equal to 0. But it could be any kind of solution you wish for. This is just one way of thinking about the problem. We can turn root finding into lots of other kinds of solutions. So we're going to focus on the simplest one and just focus on roots. So the first thing is we want to start with a guess. So we just, either just randomly pick a number, or using a figure, we can start by thinking about the region where the solution might be. And then the second step is to evaluate the function at this point. So we're going to start with x0, and then we're going to evaluate x0 with the function. And then the third step, we just talked through computing numerical derivatives. So for step 3, we're just going to evaluate the numerical derivative at this x0. These 3 steps give us enough to compute this thing. So this is, we take our guess, we subtract off the ratio of the evaluated x0 over the slope of the x0. I'm going to show you the visual intuition for why this is the right ratio. But essentially, we're looking at this ratio and subtracting it off from x0. So this turns into our second guess. Then we take that second guess, or sort of the next step in our process, x1, and then just do the same thing for x1. So we take x1, we evaluate the function at x1, and then we divide that evaluated value by the derivative at x1. And then we subtract off that new step. So this is exactly the same as this, just one step further. And then we just do this many, many times until we get very, very close. So this is what we call the induction statement. We just do this every time until the difference between our guesses gets very, very small. And we can find how close we need to be. We'll come back and actually do this in code. But this is the general approach. We just make a guess. We perform this kind of Newton-Raphson step, which you're going to have some intuition for why that's the right step in a second. And then we just perform this over and over again until our x's get close enough for our purposes. Okay, any questions here?
when our x's get close enough, can you explain that again, the final part?
Yeah, so this little thing here, is this big enough to see?
Yeah.
I can make this larger. So it's like we have, you know, our next step guess and then our previous step guess. So these are like points on the horizontal axis. And what we're doing with this stopping condition is basically just saying, like, if we're not updating our guess very much, that means we should be pretty close to the solution to this problem.
Okay, that makes sense.
Yeah, so I'll show you a picture in a second, and I think the intuition here will be pretty clear.
Okay.
So it's like, we make a guess, we don't know if it's actually that close. This thing is actually going to tell us, it's sort of like the value of the function on the vertical axis. We want to be really close to 0. We also, so if it's 0, we're not going to move that much. On the bottom, we have the slope, which just tells us essentially like, if we move a lot, if it's really steep, then this is going to be a lot smaller. This intuition I think will be clear when I show you a figure of the thing. But the basic idea here is just, if we're not updating that much, then we're close. Yeah, good question. Any others? Questions are good. Sometimes I keep track on the board how many questions you ask, and we go for records. We're early in the semester, so maybe we'll do that later. Okay, so should we do some pictures? So let's actually just. Oh no. Okay. This is not great. This is maybe better. So this is a picture of our of a particular function. So this is was this our easy function? I think this was our easy function. So you know, this is just a nice little function here. What we want to do, the visual intuition for finding roots is we want to find this point where the function evaluates at 0, and we want to find this point. So all we're trying to do is evaluate try to approach these zeros. When I start these problems, I start with a figure. I think my mind is just set up to think in figures. And I think we have big brains with big components of our brain devoted to visual thinking. Figures allow us to do this with math. So nice. So this is the function itself. We have an idea of what we're trying to do. So if I was going to make a guess, I would guess like 0.2 maybe, 0.3, just something pretty close. And then if I was trying to find this one, I would maybe guess 4.5. This is the function itself. We can evaluate this function, which we've done, and then just go through the process and think through the steps. So I'm going to show you first the sort of analytical approach to the Newton-Raphson, assuming we know what the derivative is. But then in a second, we're actually going to just approximate the derivative and do this with code. Okay, so we have the derivative. This is the easy function. We've already evaluated the derivative. And then the first step, we're just going to guess. So let's just pick 4. Going back to this picture, 4 is pretty close to this one. And it's a nice number. Step 2, we're going to find the function evaluated at 4. So if you plug this in with a calculator, that should come out to be 5. Unless my calculator was malfunctioning when I wrote up these solutions. And then we're going to evaluate the derivative. So we plug in 4 in for x, and then for x into the f, and then also into f prime, so that the slope turns out to be 6. So we can go back to our figure just to evaluate that these things make sense. This is a positive slope at 4, and the actual value is negative. So we have -5 and then the slope of 6. Okay, we plug all that in and we get 4 minus -5 over 6. When we simplify, that comes out to be roughly 5. So this is like a little bit less than 5. And if you're thinking about the picture, if we start at a guess of 5, what we're trying to do is have a second guess that's a little bit closer to the root than we were with our original guess. If we can just get a little closer in each step, then we'll end up at our solution. So we started out at 4. We ended up getting a little bit closer to 5. So maybe we overshot, but it looks like we got closer to 5 than our original guess. And if we can just guarantee that that's going to be true, then we just run this 1,000 times and we get very close to our solution. That's the basic idea. Okay, so I have some nice little slides here to give you some visual intuition. What we just did is we plugged in 4 in for our guess. And then what we did is we found not just the evaluated value, so the point, but we also found the slope. So we have both the evaluated value and the slope. What we do when we find x1, and this is, you have to spend a little bit of time thinking about the intuition for why Newton-Raphson puts us here. But this turns out to be our x1. The reason, so think back to the function itself. This is, we start at our original value of x0. Then we update that original value based on the ratio of the original value and the slope. So it's sort of like thinking about what's the fraction of the original estimated value that's made up by a 1 unit change in the value itself. So essentially, like how much of the original value itself is made up of the slope. That's some of the intuition for why we end up here. We have this value, and we're trying to move along it 1 unit in the direction of the derivative. So this is positive. So we move in the positive direction. But the reason we subtract off is because we need to move sort of in the opposite direction of the value that we're evaluating. So if this is negative and the slope is positive, we should be moving in the positive direction. So that's why we subtract off this ratio. But the ratio itself is basically just telling us how much of the original evaluated value is a 1 unit change. And then, let me just pause for questions here. Any questions about the intuition? I'm not sure I've like fully communicated all the details for why that ratio is the right one. But this is a picture of what that ratio is doing. So we're thinking about the original height, and then how much of that height is made up by the slope. So if it's a larger slope, we're going to move less far. And if it's a smaller slope, then we move further. So if this is flatter, we're going to move further. So the ratio of the evaluated value divided by the slope is going to be larger. So maybe that matches your intuition. But any questions about that? I think when I first saw this years ago, the intuition for the fraction wasn't incredibly obvious. Lots of smart people sat down and thought about how to actually like write this up so it necessarily converges. Maybe spend a second just thinking about what that fraction is doing. I wish I had this on the same screen, but this is we have the evaluated value, so the height, and then we divide that by the slope. If the height and the slope are the same number, then we move 1. And if we're at a very large evaluated value and not much slope, so if it was flat, then we'd be moving by a lot. Okay. I don't know if I've communicated that effectively to you, but that's essentially how we end up here. You can either know the intuition or know the process, but we end up much closer than we did with our first guess to our objective, which is 0. And then we just take our next guess, plug that in, do the same thing. So this is at our second guess, so x1. We also evaluate the slope, and we evaluate the value, and then we perform the same step. Except in this case, the evaluated value, so f of x, is positive, and the slope is also positive. So the numerator and the denominator are both positive, which means we want to move backwards. So we're moving, the slope is taking us away, and we've actually overshot. So we want to move backwards. The slope tells us which direction to move, and then the f of x tells us whether we've overshot or not. If it's positive, we've kind of overshot, and if it's negative, then we've undershot. So with our x1, we've overshot, and we want to come back, which puts us here. And the ratio just tells us how far we're moving. Okay, so we've gotten pretty close even after 2 passes, and then we could run this as many times as we like to get as close as we'd like using our absolute value. So when the updating is very small, then we stop. Okay, any questions here?
So
Okay, Hailey.
just to clarify, all of these are just guesses that you're making based off of the last one? Why is there no way of just calculating it? Maybe that's stupid.
Yeah. So this is, I think when you first see numerical methods, it's like, well, we have a computer that knows all this stuff. Why can't we just find it? One approach is just to evaluate the values at a bunch of small values on the domain, and then we just find the one that's closest to 0. But that's actually a very computationally intensive approach. That's what's called grid search. And sometimes we just want to be much, much closer. So it's you can look and see generally where the solution is, and then you can check at a lot of values around it to see if you can actually pick it. But sometimes we just want to be much, much closer, and this is a much faster way of getting there. With computers these days, we could do grid search where we just check a bunch of values and be reasonably close. But this gives us sort of arbitrary levels of precision that grid search isn't really set up for. Does that answer your question?
Yes.
Okay. Yeah, it's sort of unintuitive. You spent all of your life thinking about functions, and you don't really have to think about how you end up at different places on the function. But when you're doing something numerically, you actually have to think about the process of getting really, really close. And that's what we've just talked through. Yeah, excellent question. There's another hand. Yeah, who?
What if the function changes the concavity on the roots? Will this approach still work?
Definitely if we have different, the concavity is different, we would still get close. I'm not sure I understand your question. Maybe you could restate it. Oh, so if it was, if it was bowed, concave down, would this still work?
Yeah, because if it's concave down, then the slope will will it make it further?
Yes.
on
So
the second step?
yeah. So no matter the direction of the concavity, whether it's concave up or down, this will approach it. I'm going to show you a couple more examples of this. Yeah. Yeah. Great question. And you can see this. That will give you. You can sort of work through the steps with a piece of paper and see that the sign is going to be correct. But we'll talk through some more of this in a second. Any other questions? Those are both good. What are we up to 4 today? New high score. Okay, so learning this stuff is hard if you don't actually do it. So what I've done here is just write up an actual function that will iterate through and converge. So we're not going to use handwritten functions to do these optimizations really beyond today. But I want to just talk you through some of the details for how we would implement this. I think if Andy has taught you correctly, you can ask a AI agent to write this for you. But I want you to be able to evaluate whether the AI has done it correctly, and I want you to think through, be able to think through the details of how to implement these things. I think actually Eileen's question is, I think, really instructive in this way. Like, if you weren't thinking through the details of what it takes to optimize a function, you wouldn't even know that this is the thing we have to do. And you as grad students, you need to be thinking about what's going on behind the scenes. So we're going to spend the first part of class, this isn't the first part of class. We're going to spend the next part of class actually writing down the function. And then in the second notebook we'll spend today, we're going to just defer all of that thinking to a pre-built algorithm called fsolve. We spent a lot of time as a field thinking about these things, and we've already coded this stuff up. But let me show you what's under the hood. Okay, so the first thing, I've defined a new function here. I've just called it Newton-Raphson. When you're writing code, it's nice to just write it in English. You could say Newton-Raph, or you could say Newton-Raphson, and Newton-Raphson is just easier to read. So call it Newton-Raphson and not Newt-Raph. It doesn't change how fast the code runs. Then it's going to take the function. So this is the thing we're trying to find roots of. So we're just going to pass in the function. And then this is our guess, so our x0. I'm giving it a tolerance. So this is essentially Emma's question, which was when do we stop? So how close do we need to be? We're never going to be perfectly close, so we have to set some tolerance function or tolerance parameter. So this is just 0 with 8 zeros and then a 1. The next thing is the epsilon. The reason we need this epsilon is because we're going to we don't necessarily know the analytical derivative, so we need to approximate the analytical derivative with a numerical derivative. We just spent the first part of class and last class talking about how to do numerical derivatives. We're going to kind of pre-bake the numerical derivative into the Newton-Raphson. So we don't need to know the analytical solution, which makes this very flexible. So then the first thing we'll do is just set our increment x. So xx is just the guess, but for every step. So x0 is our first guess, and then xx is just going to be the guess that we continue working with. So f value is just the function evaluated at f. So this is just f of x. We have our error, which is how far we are from zero. With this first one, we don't have a second value to compare to. So the difference between our guesses is just going to be the evaluated value itself. But we'll update that later. And then we have our step count. So this is just how many times we've run this, which isn't particularly important for finding the value, but it does tell us something about how long it's run. Okay, so we're going to look at the error, and we're going to say if it's if we're outside of our tolerance, if the error is outside of our tolerance, then we're going to keep going. So this is a while loop. Are you all familiar with while loops? This is basically just like a for loop, except we're, instead of defining how many things we run over, this is just continuing to run until a logical check is completed. So this is telling us true if we're far from our guess. So if the evaluated value of f is very far from our guess, then we're going to stop. Sorry, we're going to continue. So this is saying continue if it's far away. And then everything on the inside is just, it's like a for loop. So we just have a bunch of things that are happening on the inside of the loop, and we're just going to run them every time we're far from our guess. And then after we're close, then we stop. So the first thing is the derivative evaluation, right? So we've evaluated initially, and then we're just going to check our derivative. So this is our better derivative. So this is the centered version. You could use whichever one you like. I'm just using the centered version. And then I'm just going to take a derivative of f at our guess, and then define the increment. So this is the derivative value. And then what I'm doing here is just evaluating the Newton-Raphson step. So this is the original XX. So this was our previous guess. Then we're going to subtract off the ratio of the evaluated value, and then we're going to divide it by the derivative. So this is just our Newton-Raphson step. And then we're going to update our estimated value. So this is essentially how close we are to our guess. Just by plugging in this new value in for f of x. And then we're just going to compute our error. So I think earlier I defined the stopping rule to be the difference between the two iterations. But we could also, this is an implementation just using how far the evaluated value is from 0. So either one can work. One way you think of how much updating are we doing, and the other we're just seeing how close we can get to 0. I don't remember why I wrote it this way, but this approach works just as well. Any questions about that? So then we have a step count here. So this is just updating our step count. So this is plus equals. This is just telling Python to update the step count by 1. You could also write this as step count is equal to step count plus 1. These two things are identical in Python syntax. I care a little bit if you know Python syntax, but like we live in a world of wonders, and you can use AI to translate between really any language. Is that a nice thing? What are your vibes on AI? Good? Does it make it harder to do your job, or does it make it easier?
Easier.
Easier?
But then I feel like I'm not learning as much sometimes when I use it, and then it makes it hard.
So it's maybe easier to do the thing, but then it's harder to be a student?
Yeah.
Sometimes it's harder to understand exactly what,
Yeah, that part I think is frankly really amazing.
I also think like having coding languages on your resume just don't really matter anymore
Yeah,
because you could kind of just learn any in 10 minutes. It seems like you could produce something in any coding language in like 10 minutes.
yeah. Yeah, so maybe the value of learning the code isn't as high as it used to be. The value of knowing of knowing like what's happening behind the scenes, I don't believe that's going anywhere. So we're spending a lot of time just focusing on that. I think like knowing how to think about like writing code in whatever language is also like equivalently valuable to knowing how to write mathematics, right? Like it's structured thinking, which is the thing we do at an institution like this. Like we develop structured thinking. But if it's Python or R or C++, like C++ is don't do it. But I hope you're sort of thinking through like how to structure your thought around code. These are incredibly valuable things. Even if in the future an AI will write 100% of your code, knowing how to do it is not just valuable as a skill, but for your own sort of thought process. So think about it maybe in that way. But I agree. If I'm trying to learn something new, I have to spend extra time making sure that I'm not just asking the AI to do it. And if I was just working to a deadline, I think I might not learn as much. So also be aware of that stuff. But I have definitely learned more in the world of AI than before it. Like per time, I learn more these days than I used to.
I think AI is also great for like automating a lot of busy work stuff. Like last night I had to change a bunch of variable names in this big long code thing.
Yeah.
Like it was the same code but just needed different variables, and that was way faster than I could have done on my own.
Yeah, totally.
So,
Yeah, so like automating the stuff you already know and don't really care too much about doing. Yeah. Yeah, I do just a ton of that. Okay, so this is the outline for what the Newton-Raphson is doing. We have this this while loop, which then just continues to run until we're really, really close. So I'm just going to run this. I can't remember if I defined everything above, but here's our function. And then, so I've done two different things here. So I have using the analytical formula, the what's it called, the root of a quadratic. So I've just written out the solutions to the easy function we had above. So it's like, what's it called? This thing, quadratic function. Is that what it's called? What's that? The quadratic formula. Yeah. So I just used the quadratic formula with this function and then just found the roots. And that's what these upper and lower ones are. We have two of them because it's the quadratic formula. Oh, I've even written it as a code comment. It's 10 o'clock. So I can't read before noon, apparently. So we have the high root, the low root. We have two of them, so we want to think about both of them. So I'm just going to run this. This is the two analytical solutions. These are like very precise, and they're analytical. So these are the things we're trying to target. But then what I want to do, I've just written some code here to give us some of the information each time we run the approximation. But I'm going to give it the easy function. So this is the thing we have the analytical roots to. So this is the high and low. And then I want to run the Newton-Raphson approach to see how close we get to the high and low roots. So this is Newton-Raphson. I'm giving it the easy function, and I'm giving it a starting guess of 200. When I run this, it says easy f is not defined. So it looks like I actually didn't define these things above. So we have our easy f, which is here. and the derivative, and then we'll work with the medium in a second. Okay, so when I run the Newton-Raphson, better derivatives not defined. Okay, so that was from better derivative. Here we go. So we wrote a better derivative using the Taylor series expansion for our derivative definition, but you could write using our original definition if you like. And what we have here are the actual analytical roots, and then we have the output for Newton-Raphson. So the way I've written the function in the cell here, I'm telling it to just specify the starting value. As you'll see in a second, this actually does matter, like which starting value we pick. So I'm just, I have the output showing the starting value. Then I also have the step count, so how many iterations did it take to get really close to the root. And then I have the root value itself, so xx. I just have return none for completeness, but you could drop that if you like. Okay, so so nice. So let's just check our solution against the roots. So we were at 200, which means we were above both of the roots. So through our Newton-Raphson approach, we started out at 200, which is very, very large, and then we moved our way towards the high root. And you can see it took us 11 steps, and we got very, very close. So this is, someone can check how many decimal places we have, but it's at least, what's that, 6, 7, 8, 9. So 9 decimal places, which is really close. For all practical purposes, this is identical. Okay, so this is nice. We can change our tolerance. So if we want it to be even better, we could set our tolerance to be even closer. And this would get us, what's that? It's like 3 or 4, maybe 5. No, these are exactly the same. So this is exactly the same number as the high root. So at 12 decimal places, we've got exactly the same number as our analytical solution, at least rounded to the thing that's being printed out. So you can set arbitrary closeness. What you'll see though is we ran one extra step. So the level of tolerance is related to the number of steps we run, as you'd expect, right? So if we want to be really, really close, we have to continue running even further. But this approaches really quickly. This is 11 steps or 12 steps. If we were to do the grid search, this would take us, you have to, so it's a grid, if we're searching at this level of resolution, we're breaking up each integer increment into that many steps. So it's like 0.0 with 12 zeros, and then you have to break up every one number into that many increments on the horizontal axis. You can do the math there. That's just an incredibly large number of things. Here we did it in 12 steps. So this is just a much faster approach, which is why we use it. Okay, any questions here? Great. So what happens if we change the starting value? What's your intuition here? Let's say we started at small values. So we started at negative 200 instead of 200. Do you have an intuition for what's going to happen? Are we going to converge? Lauren says yes. The answer is yes. We will converge. But let's test this. So what I'm going to do is, so I'm printing out the actual values. So these are the analytical roots. And then I'm going to start at 200. Let's say I start at negative 200 just for symmetry. Same tolerance, and then I'm going to run both of these things. So the first one with the starting point of 200, I ran this in 12 steps, and I got this number. So this is really close to the upper solution. And then for the second one, I ran this starting with my initial guess at negative 200, ran for 12 steps, and I got a different value. But what you can see here, both of these are the roots. It's just because there are two of them, we ended up at different solutions depending which one was sort of closer in a certain kind of way. It's not necessarily that it's closer on the horizontal axis, but we get this sort of movement of convergence towards one of them. And depending which direction we're coming from, we hit one of them first. So we started at negative 100. We start on this side, and we sort of converge until we stop at the lower root. Starting at 200, we converge towards the upper root. And then you could pick some intermediate values. So what do you all expect would happen if we started at 2? Upper or lower? Hands up for upper. Hands up for lower. And the rest of you abstain. All right, I see you. Lower. Yeah, so you can see this from the figure. This is the local minimum. We're below the local minimum, so we're going to get closer to the lower root. Okay. Any questions here?
So the goal is to find both roots or just one?
So that's a question. If I were trying to if I was trying to think about roots to this problem, right? Like what you're trying to do is think about like whatever the problem is representing. And if I'm thinking about this as like equilibria, the roots would correspond to like an equilibrium solution. And I might care about one of them, but in general, I would care about both. So knowing the sort of full scope of the problem, often you'll care about solving for all of them. Like which one matters to you? Well, kind of both. At least in most cases. Maybe one of them will be more important to you. But even in that case, you'd have to think about how do you avoid the other one in your solution approach. Any other questions? All right, nice. So I want you to get your hands on this medium function. So do you like doing actual work in class? Some no's. Respect the honesty. This is the medium function. So all we're doing is taking the easy function and then multiplying it by this thing. What I want you to do, we're going to spend a few minutes here and then we'll take a break. I want you to find the roots between -1 and 10. So I've made a figure here. There's a reason I'm asking for this specific interval. We're mostly trying to find this root and this root. This is actually a lot harder to find the analytical roots, right? Like before we had the quadratic function. You could take the function and plug in, like how would you invert it, right? Like just think about the difficulty of, like it's a little bit harder than the last one to find the zeros of this function. Okay, so yeah, we'll spend a few minutes here. Think about trying to find these roots. I think this maybe should take like 2 to 3 minutes. I think you all are capable of doing that. 2 to 3 minutes, find the analytical roots. Think about how many there are and how you would find them simply using this figure. All right, it looks like no one's really typing anymore, so I'm going to take this as you've all found the roots. I also wanted to show you, if you're using Colab, Gemini is built in, so you can ask Gemini to help you in the notebooks. This is really nice. One of the benefits of using Colab. It also can get in the way sometimes, but if you get stuck, Gemini can see your entire notebook. So I want to talk you through how I answered this question using Colab, using Gemini, and then we'll talk through the actual details of the thing. Yeah, Emma?
Did you, I don't know, could be wrong, but on Monday I thought you said that we shouldn't use Colab.
You can use whichever one you like. I hoped what I communicated was what I do on my computer in my office is use Anaconda. Yeah, and I think most people have Anaconda. But you're more than welcome to use Colab if you wish. What you should do is go up here to File, and then if you want to use Colab, make sure you're saving a copy for yourself. If you just run what I have, it won't save for you. That might have been what I was saying.
Okay.
Yeah. Just make sure you save a copy in Drive before you run it. Which is actually what I'm doing here. So I'm actually not running the file that opened by default. Saving a copy. Yeah. Did I make that clear? Maybe I didn't make that clear. At least it wasn't clear to you. So.
Yeah, no, I just thought that you recommended doing the other one, but then I'm not really familiar with Colab.
Yeah.
But if it has like Gemini built into it, I didn't know if you wanted us to use that.
I don't have a preference either way for you.
Okay.
I think in terms of like ease of use, in some ways, Colab is better. But in terms of like keeping your files organized and referencing your local data sets, I think Jupyter through Anaconda is the better approach. That's what I do everything with on my computer, is Anaconda distribution of Jupyter. Okay. Any other questions? I think there are ways of running LLMs in Jupyter on your local computers. I've never done it. I use a different approach, but that could also work for you. So what I did, if you're in Colab, I just opened Gemini and then just asked it find the roots between -1 and 10, and it looked through my entire code, knew the context of what I was asking for, that it was asking for the median function, and then knew that I had written a hand-coded Newton-Raphson, and then wrote me this. So this is the Gemini output. It turns out in this case it's very good. Here we have the Newton-Raphson giving it the median function, and then we're even getting some indication that that we just should start near the lower root just from the figure. So we have the lower and we have the upper, and then if we run this, so we'll accept and run this, then we get our 2 roots. So we don't actually want the easy roots. We want this. Okay, so nice. So this is, this is pretty close to the original one, but it's slightly different because we're multiplying by the exponent, the exponential function. Nice. So our lower root, this thing should be, about 1/3, and then this is roughly 4 2/3. So 4 2/3. Okay. Any questions here? You feel comfortable with this? All right, love that. If we ever go too fast, let me know. If we go too slow and you get bored, also let me know, and we can just crank this up to 1.5 speed. I've been practicing. You want to hear? No one does. Okay. Me either. So this is nice, but we also know, just looking at the functional form here, as we take the limit as x goes to infinity, this thing will be dominated by this, whatever lambda is. In the function, I've defined lambda to be 1/10. So if I just plot the entire figure zoomed out, what we've been working with is right around 0. So this is, for small values. But we also, we get this, the quadratic dominates for small values, but then as x gets large, then the exponential, so the exponential decay function starts dominating, which means we get this asymptote towards 0. And this actually presents some tricky challenges for the Newton-Raphson, as you'd expect. Maybe expect. So if you're thinking about what the Newton-Raphson does, and the reason we're walking through this is because behind the scenes, you need to think about these things. Even with the pre-built solvers, you need to think about what the Newton-Raphson is doing so that the outputs make sense. When we do these numerical optimizations, it's not quite as simple as the linear ones. So if I were to plug in 50, what's your just intuition about what happens with the Newton-Raphson as it starts approaching? Where do you think starting at 50 is going to go? Going to go this way or this way? So starting at 50, and why would it go this way?
Because there's no root on the right, it's just an asymptote, so the closest root is to the left.
So the closest true root is to the left. So our closest true root to 50 is here. So we would want the Newton-Raphson to go to that upper true root. Any other perspectives here?
Is it just going to continue moving towards infinity on the right because you don't have, it's just it's not going to solve it. It's just going to keep moving and trying to find it. It's not there.
So Eiley has identified what we would want to happen, and Lauren has identified what will actually happen. The Newton-Raphson is just a hill descending algorithm. Like, we want it to get closer and closer to 0, but what it's actually doing is just following the landscape downhill. Yeah, Gary.
If you like raise the tolerance, would it stop at some point when the asymptote gets closer?
Great question. So we're actually going to explore this with our working with this with our tolerances in a second. I'm sorry, I called you Garrett. Remind me of your name, Kevin? Yeah. So Kevin's thinking about the tolerances and what happens because we don't have a true root off to infinity. So what happens in that case? Okay, so Newton-Raphson is just a sort of, I mean, it's sophisticated in some ways, but it cannot just go out and search the entire landscape. We could do grid search, but that's not what Newton-Raphson is doing. It's much more efficient, but it is really only thinking about hill descending. So in this case, if we were to run Newton-Raphson starting at 50, we get this thing. So this is 310, which is way off to the side. It ran for 23 steps and ended up here. So this is telling us a couple of things. First off, it did converge. The Newton-Raphson ran and then ended, which means we've satisfied the ending condition. Right? We got close enough to 0 for our tolerance. Let me show you two other runs. So here I've increased the tolerance by 2 decimal places. For this second one, it's the same guess, same function. It's just the only thing I've changed is the tolerance. For the second one, it's run for 28 steps, and the actual estimated value is much larger. So we've gone up by like 53. So this is telling us that we're probably not very close to a root. We change the tolerance, we move a lot. And you can see why in the figure, right? It's an asymptote. So as we continue to increase the tolerance, it's going to get further and further into the asymptote. This last one, we can run it, it's going to get larger again. So this is one of the pitfalls of Newton-Raphson. And you have to be aware of this when you run these kind of solvers. So does this answer your question, Kevin, about the tolerances? Or was it different than this?
Yeah, I think so.
Okay.
I think that answers it.
Okay. Yeah, so it's like when we think about what the approach is doing, it's really just descending, and when we run into asymptotes, there is no root. There's no value that's exactly equal to 0. So setting the tolerance gets us further and further out to infinity.
Can you
Yeah, Eiley.
explain again why the tolerance can't just be 0? Like, why do we have to make it a small number again and not just 0?
Yeah, so if we were to set it equal to 0, I mean, first off, computers can't really handle, like, you're never actually going into the Newton-Raphson, you're never actually going to exactly equal 0. You could round it, but that's effectively what the tolerance is doing. It's like saying, like, what level of rounding should we use?
Okay.
You could set it to 0, but I think it would never actually stop.
Right. Okay.
Does that make sense?
Mm-hmm.
And I think to think about why that's true, you can go back to the definition of the Newton-Raphson. And think about what this ratio is doing. Yeah. That's the short answer. I'm not sure if that's like fully answering your question, but that's the general idea. Like when we're dealing with small increments, computers just can't really handle perfection.
Okay.
So when we're setting up the tolerance, setting it equal to perfection, computers are going to be upset about that. Yeah, Kevin.
Is it like same idea as if you're in like a distribution function, if you say like probability equals an exact number, it's always just gonna be 0. Is that like saying, like, can you think about it that way, I guess?
Yeah, I think in a sense, when I mean, there's sort of similar ideas, like thinking about the incremental versus like perfectly instantaneous, and that general kind of distinction carries over a little bit. Like if you think about in the probability distribution, an incremental value does give you a positive, like it's a non-zero value. So I guess in that way they're kind of similar, yeah. But I'm not sure thinking about it in that way is necessarily like the easiest way to understand the problem. Yeah. Any other questions? New high score for question count. I've even lost track.
So since there's no root to the right, how close do you have to be to the true root on the left for it to actually count? Like,
Yeah, very good question.
where's the line?
Yep. So what if we plug in something like 25? Let's try 25. It's going to be right around this max point, which sort of determines which direction of movement in the Newton-Raphson because of the slope. So if you plug in like 25, let's say, then we get a large value. If you plug in 24, so 22, so wherever wherever this maxima falls, that determines the sign of the slope, and that would determine which direction it's falling. So you can sort of think about like dropping a marble somewhere, which direction it's falling is determined by which side of that peak you hit.
Okay.
Any other questions here?
So we see that it's just like, it just keeps getting bigger as we keep time. That tells us to go in the opposite direction.
Yeah, so so this is one of the heuristics. If you keep changing the tolerance and you get very, very different numbers, then you know you're in something like an asymptote. You know the solution you're getting is not a very good approximation. Yeah, what else?
Sorry, can you scroll down to when you put in like 22?
Yes.
Why is it doing the first root instead? Isn't the second root like 4 point something? Wouldn't it be closer to that?
Oh, good question. I'm not sure. So the first step is going to be a very dramatic move. And maybe what it's doing is overshooting. But you're right. So if we start at 10, for example, then we end up here. And if we start at 22, we do end up overshooting. So one of the steps in the process is jumping much further than we'd hope.
Okay.
So part of the problem here is the sort of the size of the steps. That's a great question. Yeah. What else? So we've been going for an hour and a half. I want to take a break. Can we do two things before we take our break? The next thing I did here to sort of try to account for this is to set a Newton-Raphson function with a maximum number of steps. Like, what's happening here is we're going out to infinity, and to get us exactly equal to 0, we would just never stop. So depending on our level of tolerance, we could have a very large number of steps. Like 23 is a lot of steps, actually. 32 is a lot of steps. So I defined a function with max steps, which just allows us to control for asymptotes. Like if we're in an asymptote, we're going to have a large number of steps. So we can cut off the possibility of an asymptote with a step count. So the last thing to do is just, the only real addition is, in addition to the error being within the tolerance, I'm making sure that we have to be below some step count. So this is just a joint condition. Both have to be true for the while loop to continue. And all I'm doing is just adding a step count. It needs to be less than our max steps, whatever we define that to be. And then if we hit our max step counts, and you close your loop on your Apple Watch. Oh, thank you. Yeah, there we go. I don't have one. That's what people say. Then we just add a print count telling us that the max steps have reached and we haven't hit convergence. So if I run this, it runs 76 steps, and we should exit due to non-convergence. So we censor it down to 50, which tells us that we haven't actually converged. Okay. Any questions here? We're just making our Newton-Raphson a little bit better to capture this asymptote. And then the last thing I want to show you, I think this is the last thing. Let me just show this quickly. This is just another fix to the Newton-Raphson, which is built into the pre-built ones. All I'm going to do is take our medium function, but then shift it up by 1. And all this is doing is just making sure the asymptote doesn't hit 0. So we're never actually going to be that close to 0. So what happens in this case? Think about what the function is doing. If we start at a large value, Newton-Raphson is going to drop the hill descend. And it's going to hill descend until it gets close to 0. But here, it's never actually going to get close to 0. So it's just going to continue forever. So it never will actually, it will never actually get close to 0. If we run this, I'm going to run this, and we end up getting this this nan value. This is Python speak for I don't know how to compute a number somewhere inside. The reason is, think about what happens when we get incredibly far out. We get a slope that's very close to 0. Right, so in the asymptote, the slope is really close to 0. But the evaluated function is essentially 1. So in the Newton-Raphson function, we're dividing 1 by something that's essentially 0. Which means, like as we get further and further out, we're going to round the slope to 0. So we're dividing something meaningful by something 0, and eventually Python doesn't know how to handle this. So we get a nan. So that's something we should probably fix. So the derivative gets closer and closer to 0, eventually rounding to 0. So we have to account for this. And this is just a bit of a technicality, but we need to make sure that the derivative isn't 0 or nan. And so I've just added this little catch inside. Okay, so if we use this instead, then this will tell us that the derivative is not defined. It's stopped after 40 steps, and this is the last guess for x that we found, which is just really large, and tells us we're really running into a lot of problems. Okay, so I told you last thing a couple of times. Maybe we'll come back together after our break and talk about the professional solvers that use Newton-Raphson behind the scenes. Do you like 10-minute breaks or 15-minute breaks better? Hands up for 10. Hands up for 15. Are we going to go by democracy or benevolent monarch? Maybe we'll alternate. Next time we'll take a 10-minute. Today we'll take 15. So that's, oh boy, 15 minutes from now. You do the math.
10:52.
Thank you. I've been talking for an hour and 37 minutes, so I can't do math. 10:52, we'll come back together and we'll close a few things out.
I just or like asking to schedule it. Oh, I hate that. So I don't know. It's so stupid.
I don't wanna do it.
It's so awkward.
I also
I
like
didn't
didn't
do
research.
my life. I don't. Because for so long I was like, right after I graduate from MGB, I'm going to New York City. And like whatever. And now I'm like, I think I'd rather die than live in a studio bedroom and have to sell my car. And all that stuff. Like I just don't know.
Two of my friends moved to New York, one with a job, one without. And she's still
to New York without a job.
Yeah,
It's
that's
like,
crazy.
I know.
Do they like it?
I don't think they should have done it, but I think they just needed to like get away from home. Her parents said that they would like help her for the first 3 months. But my thing is like after you can't get a job for 5 months, they start serving like
Yeah.
do something.
Yeah, my cousin.
Wait, she's not doing anything at all?
No.
Oh.
And I'm like, and
Oh,
she's
wow.
too like prideful to ask. I'm like, I'm gonna get a job based on like a connection. Like I'm not gonna get a job
That's where I'm
raw.
at this point. Like there's no, out of time to two, ready, just like somebody who like isn't working at all, so I'm just like talking.
Exactly. Exactly. And all of like she's my friend's best friends, like there's so many of our friends' parents like help and like all that stuff. But she like wants to get it like quote unquote on her own, and it's like
That's
you don't get a golden
Yeah.
star for doing that, by the way.
Yeah. And then you just don't get it at all. If you
Yeah.
do that.
And then you end up in New York with no job.
I also like have a summer camp that offers me a job and I'm like, do I do what?
Yeah.
It's just silly summer of not actually doing the work. Who knows?
I mean,
Because then I'm just like, I feel like I'm getting anxious the whole time about how I don't have a job lined up. And I like asked in an interview, I was like, I need like set aside job search time if I take this job, and they were like, we can do that.
yeah.
But I just know that I'm not gonna actually do that.
Oh my God. I'm at the point in the job search where I was over this spring to my dad on the chill, and he was like, no, I have a call with the tax policy center later. Why don't they offer them your service?
Your services. We all just become accountants.
How terrible.
I think we should all start our own company. Together. We could tutor future MQE students.
Yes.
You can tutor Maxine.
Yeah. We're just like, I don't know, looking up on Claude.
I want to generate your exam questions. But no, I was just like, let me just put the plug in. I was like,
You're doing the tech council capstone. Can you send me that link tomorrow?
yeah.
How old is she?
She's 10 months and 8 days.
I just think I like Pittsburgh.
You do?
Yeah. Like I think maybe I'll see. I'm not from here.
That's also surprising.
That's not what I meant. I love Pittsburgh. I mean,
I think maybe I just don't want
I've
to.
been here for 5 years.
Yeah, we'll see. But
Yeah, I guess you have as well.
I'm coming from New Hampshire, so anything sounds great. I'm like from farmland, so.
No, you should definitely reach out to her. She has like great connections.
Yeah.
And if you apply to a job and you tell her that you applied, she'll, if she has like a
She
connection,
said
she'll
that at the happy hour, yeah.
help you. Her email is, she's literally the sweetest. And she was like,
She's the
like, I don't know if you ever had a video, which is awesome. But she was, I didn't know she was a teacher for like 30 years.
That makes sense.
Yeah, no, she was so sweet.
I just think that I should be able to walk down the street and someone should say, hey, do you want a job? And then I'll get one. I don't think I've done anything except bookmark things on Indeed. I haven't done anything.
Honestly,
Yeah, because I'm back.
Yeah, no, I was like,
It's like I was saying things only in New York, and then I got to a point where I was like, I don't want to live in New York. Like, I don't want to do that. And so now I just have a bunch of things saved that I don't want to apply to.
I eventually don't really want. I don't know if I want to like stay in Pittsburgh for another year and like live with my current roommates and like try and find a job here and then move like either back home or like DC or like another East Coast city, or if I want to just like move back home right after. Because I feel like with the like MSP help, the place I'm gonna get a job is in Pittsburgh. But I don't like.
Yeah. Well, I think Stage is not going to help me at all with the way I don't respond to her emails.
She's actually reading like recommendation letters.
Yeah.
Could you send us application for a lifeguard position?
Or she'll send things that are like 10 years minimum experience.
Yeah.
Like,
Required PhD.
Yeah.
experience.
So she's always surprised when she sees me. Like she's like, oh my god, you're here.
I wish Riv was agile, which is insane. But they just brought in Megan, and then I asked Megan when she came to do the alumni chat. I was like, oh, are they gonna hire more people? And she was like, no. I was like, alright. Who said that? Ben said that? Oh my god. Why would he say that? In front of her? Yeah,
All
like,
of my friends were doing administrative work in their jobs, and I know that's what like happens like at like a baseline job usually, but it's like one of them works for a lobbying firm and two of them work for lobbying firms, and they call themselves like the job description is like legislative or something like that, but they have them just like writing memos and like it's stuff that Claude could do,
yeah.
and it just like it sounds terrible.
I have one friend who became an accountant, and now she was supposed to come visit this weekend, and she's like, it's tax season, I can't. And I'm like, if that's my life someday, like, actually, like, whatever. And then my other friend was in data analytics for Amazon, and then they mass layoffs, and then he got fired. So I just not really.
Do you guys remember when they did that big Tesla layoff?
Yeah.
Yeah, two of my friends had jobs at Tesla, and they both got fired immediately.
Amazing.
Also, two of my friends did remote work for like government contracting, and then with the new rule that you couldn't do remote work, they either had to move to because they were doing like completely remote, they had to move to the city that they needed to be in or lose their job. I think did they fund online security?
I'm just gonna throw away my phone and go camp in the woods forever. Not talk to anybody ever again. And not work. Exactly. We're just gonna disappear into a national park.
See you on the news in like 20 years.
Eaten
You're like,
by mountain lion. Unwashed demon.
I would love for you to be like a survivalist. I think that would be really cool.
I think you'd be good at it.
You want to know
I
what
think I
happened?
would survive too.
My brother was, I've like collectively has been looking for jobs, and my brother applied to be a ski, like in Colorado, like a ski lift person, and he didn't even get that. It's like Jesus.
I saw a thing for going and working in Antarctica with penguins, and I was like, maybe I should apply to go to Antarctica. It's like run the gift shop. I'm like in Antarctica.
I could see myself doing that. No, I also thought about applying to work at the zoo.
Why?
Like,
This is cracking me. Why didn't you want to recruit me then?
Did she email directly to us?
Yeah.
Can we talk about Kathleen asking us to be on that panel and her stage responding being like, we have our own panel that day. None of them can go.
It's been scheduled for some time.
Time.
I was like, I've never heard of that.
What is?
I think she sent it out in like December, so like nobody remembers.
Yeah, I remember the beginning of the year was like mass scheduling.
Yeah.
We're in base camp and all of our phones are like buzzing every 2 seconds. Calendar invites.
I hate Outlook too, so I like never looking at it.
I don't think I've ever looked at
And
anything
then
on
you
the
have
calendar
notifications,
ever.
like 30 minutes, it's 30 seconds.
I think I went to half the career chats. I forget. I went to the one that I had to lead.
That's an accomplishment. I submitted the same questions for all of them.
I don't know why I didn't think of that. We should have all done that.
No, they're supposed to be like catered to the person.
No, but your questions were good.
Well, that's
You would
because
also
I
be
was
like chatting with them about other stuff, like the abundance of it.
I did go off on tangents with a few of them. I'm not good at like talking about what we're supposed to be talking about. At that happy hour, I talked. What was the guy, the representative? You were there for like 10 minutes. I was giving him bar advice in DC.
Well, he was asking me. He was like, "What's a good dive bar?" I was like, "I'm ready this guy."
The Rivers Agile guy was asking about dive bars.
No, he would.
He was non-profit. If you found him to go to,
Yes, he was like just show up.
Oh my god.
Dude, just whistled. But he was like just show up to, what's it called? Like just show up to something you're not invited to and give people, like introduce yourself and like
What
pitch
in the
yourself
world?
basically.
What alternate universe is this where we have to just bar
Dave was like,
shit?
"You guys get so good at the happy hour."
No, he said that to us too, and I was like, I talked to one guy for 10 minutes. Thanks, so.
I wonder if he went to the bars I recommended.
And John said, "No."
Wait, Emma, who was this?
Bet.
He just said that he was going to DC, and I was like, okay, you have to go here. And then he wanted to find a dive bar. I hope he went.
I think I'm just gonna start walking in places and asking for the CEO.
I was talking with one of the guys, and he's like, "Yeah, there's always the option to go to like physically walk into the place and give your resume to the receptionist, but nobody ever does it. So you can be the first option."
Oh yeah, oh my god. No, but when you do go in, because in high school I was like, I need a serving job so bad, and I was applying to places online and no one was getting back to me. So I was going into restaurants being like, can I work here, basically. And then they were all like, we have online application. And I'm convinced that's what's actually gonna happen if we try going in person. They're gonna be like,
I love the application. Come on.
The guy seemed to say
What
that it was
company
like
is he from? I'll
it was
go say
CGI consulting.
Just go find him.
what did they do? Something.
Consulting. It's like tech consulting. Is that what you want to do?
No,
No.
I don't wanna do any of this.
It's like all the stuff.
I wanna do this class.
That's it. I'm gonna just keep on getting masters.
I mean, you could do that.
Yeah, true. I'm just gonna come back as an MQE professor. I'll take some time. Just come back.
You have two options: become a survivalist or teach an MQA.
Or I could be a UTA forever. I'll come back to undergrad. My peak.
I mean, I'd love that.
Yeah.
You could coach dog sledding in Norway.
Oh, no, I was not good at it,
Yeah.
unfortunately.
Yeah, you could
Always be a lifeguard.
Yes, I'll feel like
Is that real? Are you guys serious?
Yeah, there's like recruiting of that group beforehand.
$17.50 an hour to lifeguard at the Shenley pool.
Oh, thank God.
They just sent it to us.
Amazing.
What?
Yeah.
She did?
Yep. She was like,
Yeah.
these are some jobs you guys might be interested in applying to since everyone has been struggling.
When did you do that? I wonder if we're like,
Lifeguard
the
at Shenley
worst
pool.
school.
Did
No,
not
after
see that.
Kevin was mad at us in the fall, I think we've just gone down.
No, I'm just thinking like I
And
wonder
also,
if
like, you
every
check the stats of jobs you apply for, and like a non-competitive job has 450 applications.
Yeah.
Like it's ridiculous.
But I wonder if like the other cohorts were like able to like did most of them have jobs by now? Are we like
Isn't there like a 98% job rate
Yeah.
upon graduation?
off the website? We're the reason they have to remove that stat. Shoot.
Drop us.
It was an outlier.
No, okay, that's good.
And what do we
Got
do
it
now?
up his nose. That's a reply.
Yeah, that's, yeah. I
I'd-
saw a video today that
I'd be
somebody
very
auto-applied to
surprised.
6 million jobs.
6 million?
And
How are
he
there
got-
even that many jobs out there?
And he got, like, most of them didn't even respond to him. Then he got like 2 million rejections. And then he got like a few thousand first round interviews, and then like 200 second round interviews, and then 12 out of 6,000 final round interviews, and then 3 offers. I mean, out of 6 million.
That's
So,
so tough.
yeah.
My personal perspective, I haven't followed past years' placement records, but I'd be very surprised if people had gotten jobs by now. So
That makes us feel a little better.
Yeah.
yeah, but that's just finding a job just takes a long time, and finding the job you love takes a very long time. So expectations. I'm not a professional placement officer, but that's what I would expect. Y'all want to do some more work? Take your mind off jobs. So this is going to be maybe less funny than your conversation, but what we just did was set up Newton Raphson, right? We were thinking about some of the like hill descending algorithm problems. The last thing we did was find that when there's an asymptote that doesn't go to 0, then we end up with these nans. So like it doesn't actually converge to 0. So we just set up a Newton Raphson that doesn't have that problem. We just tell it that the derivative is not defined, and then we stop it eventually. So we've done all this work, right? We can write these these functions to do the thing by hand if we wish. And the important thing with thinking about these problems is that you understand what's going on under the hood, because the professional versions don't solve all of the problems for you. And I'm going to show you a professional solver that does still encounter some problems. There isn't a perfect way of doing this. If you find one, you can add it to the Python library. Someone would love for you to do that, and maybe that's your job. Okay, joke didn't land. All right. So the one we're going to use quite a bit is from SciPy. So if you're familiar with Python, SciPy is just like the scientific Python library. It has a optimization package, and then we're just going to import fsolve. Fsolve is basically just like a fancy version of Newton Raphson. So the first thing I'm going to do is just run this. I'm going to give it the medium F2. So this is medium F, but we're shifting it up by 1. And then we're going to start it at 1. When I run this, I get a full output. So we're specifying that it gives us the full output, which tells us a bunch of things. The first one is the solutions. So let's see. Our original Newton Raphson, if we were to use our hand-built Newton Raphson for solving medium 2, so we could do Newton Raphson and then give it start it at 2, like we did. It's going to find the same number. So we're just verifying that our hand-built one and the professional one give us the same solutions. So this is the route that it finds. It has a bunch of other things down here, but importantly, it tells us that the solution converged. So we do get convergence with this. But we really just want the root most of the time. So I'm just going to get the first entry. So this is the Python notation for getting the first value in the array, and then I just want to get the actual value. So we just put on item on the end to get the number. Any questions here? Hard pivot from thinking about your summer. So one thing we can do is just go through almost like a grid search, but we're just going to take a bunch of values and then start the Newton-Raphson at a bunch of different integers from -100 to 101. So we're going to look at a range and then start Newton-Raphson at each one of these values. So this is just a for loop inside of a list. So we have fsolve. We're putting in medium f2. We're giving it a guess of x0, and then telling it to give us the full output for each one of them. And then we're just listing out x0 for a huge range of these things. And then we'll just run this. So this is getting all of the roots, starting at each one of these different starting points. So we're essentially like starting at each integer from -100 to +100. And then we're just running the Newton-Raphson on that. And then we're just going to get the values. So this second thing is just going through and getting the actual values for each one. You could merge these together if you like. And then I'm just going to take the list of all of the rounded values and find the unique ones. So np.unique, just we're rounding each one, and then we're finding the unique values. So it'll just remove duplicates. And if I just print these out, you can see the unique values. Someone tell me what's going on here. Why do we have like 80 of these things? Yeah.
Are all those values within the tolerance?
So maybe a lot of these are within the tolerance. So we see like, this one and this one are pretty close. So maybe these are within some tolerance of the truth, and our rounding just hasn't gotten us, hasn't like merged those into the same unique value. So that's one possibility. What I'm going to do is actually just evaluate each one of these to see what the actual evaluated number for each one of these is. If these are close to the root but are slightly different, then we would see most of these showing up. Once we plug them into the function, they would evaluate to 0, right? If we're close to the root, these should be close to 0. If they're not close to the root, then something else is going on. So what I'm going to do here is just put a bunch of these functions, a bunch of these values into the function to see if we've gotten the root. If the value comes out to be 0, then we've gotten the root. And if it comes out to be some other number, then something has gone wrong in our convergence. So what do we see here? So the first, I guess that was a rhetorical question. Yeah, we're like 2 hours into class, so my attention, if I was a student, would be hard to hold. Teaching is a very different thing, so most of these are 0, right? Like a lot of the first ones are 0. Then we found values that are very much not 0 for larger values. These are actually like 83, 84. And then a bunch of these afterwards are 1. So something has gone wrong with a lot of the root finding that our professional solver has gone through.
Why are we having -0?
Yeah. It's a good question. So -0 is so Python sort of treats like slightly above and slightly below 0 as slightly different. But in practice, it's 0.
It's zero.
Yeah, so that's what that's. Yeah, -0 is just, Python is weird and gives you like a slight distinction between positive and negative, like depending where it's been rounded from.
It's like 0.0001 versus negative 0.0001.
Yeah, exactly. We've done some rounding here, behind the scenes, or front and center, I guess. And some of these are being rounded up and some are being rounded down. Yeah. Okay, any other questions? Okay, so let's just go through and take a look at what's going on. I especially want to pay attention to these 80s. So the function itself, if you scroll back up, when some of the values converged to roots, and these were the first ones. So when we checked starting with a guess that was low, we ended up getting close to the roots. But then there were a bunch of guesses that ended up with solutions around here. So the evaluated final guess was in the 80s. Anyone know, like, what's the intuition for why we would end up converging to a point on the peak? Like, this is nowhere near a root.
At that point, our derivative is 0, so it's like kind of getting stuck there.
Yeah, right. So that's exactly the right intuition. Like, for the Newton-Raphson, what it's doing is dividing the evaluated value by the derivative. And we talked through, like, when the derivative is exactly 0 or close to 0, that gives us an error of division, right? If we're dividing something by 0, we can't really do anything with that. So what's happening behind the scenes is the fsolve evaluator is getting stuck. It's like stopping at these values. So we end up with some problems here. And then the rest of them all, so if we've like started far enough out here, the rest are just going to converge off to infinity, or not converge, but continue to approach positive infinity with an evaluated function at 1. So a bunch of these are just in the limit, or going towards the limit. Okay, any questions here? So what's the point? Well, this is how we think about finding solutions to really any sort of arbitrarily complex function. We can find roots using different versions of Raphson-Newton, Newton-Raphson, and it works pretty well, but I want you to understand the process for like what it's doing, because that informs how you think about the problems it can encounter. And I've just shown you, like, this is not a particularly complicated function, and we still have to think about the nuances for how it's giving us solutions. So be careful and make sure you're checking that what you actually have is a root or a solution to your problem. Okay. So this is part 2 of numerical methods. We started by thinking about derivatives, and then we walked through how to find solutions to equations. The last thing we're going to do in numerical methods is work through numerical optimization. So, like, so much of economics is about theory and maximization problems, right? Like, we can set up lots of our economics problems as optimization problems. We love this stuff. Do y'all love this stuff? Optimization problems? Personally, I find it very satisfying. And I love setting up problems as optimization problems. But again, the core problem we're trying to solve in numerical methods is when we have problems that are so difficult to solve that it's either not worth doing or it's intractable. How do we then solve these problems using a computer? So we're going to focus on the last part, which is numerical optimization. And I think we're not going to get through all of it today, but we're going to set up the fundamentals. The basic idea is we're going to take the same sort of first order conditions that you're familiar with from like Kevin and Richard. You had Kevin and Richard in the fall. Is that right, for like theory and like game theory stuff? That's nice. Y'all love that stuff?
Game theory, not so much.
Okay. I love game theory. But yeah, so a lot of that kind of approach requires solving optimization problems within some structure, right? So you have like people making decisions, and then in a social setting, and then you play everyone against each other. And that's usually like a best response function, which is often a maximization problem. And the basic idea looks like this, right? So our first order conditions are just finding the derivative and setting it equal to 0. So if you have some function that looks like this, what we want is for the derivative to be set equal to 0. So if you're noticing similarities with what we just did, root finding, that's where we're going. So if we're thinking about the first derivative, we want that to be equal to 0. So every solution to an optimization problem is finding the root of the derivative. Okay, so this is just your picture, really nice. And then we're trying to find the places where the slopes are 0. So the first approach is, we can call this option 1. So if we have a function that we can find analytical solutions to, we can just use the analytical derivative and then root find on that thing. So I have two functions here. We developed our ideas for fsolve. So we have this function, which is our easy one, and then we have our medium one from the previous notebook. And we can find the derivatives for both. We did this in the last notebook, but if we have the analytical derivatives, then we can just think about the solutions. So for the easy one, we just want to root find for the derivative function, right? So we developed all this mechanism for finding roots, and it turns out that root finding gives us the tools to maximize a function if we know the analytical derivative, right? We just find the root of the derivative, which gives us the maximization, the optimization for the function. So that's nice. So in this case, what I'm going to do with option 1, if we have the analytical derivative, is just fsolve the derivative of f. And when I'm thinking about this problem, I can look and see, for small values, we're going to converge as long as we pick a nice little guess. So using fsolve, not our hand-built Newton-Raphson, but the professional version of that, we get a solution that's so our x star, so the maximized version, or the maximized value, is at 2.5, and then we can plug this into our function to give us the evaluated value. So we just plug 2.5 into our function, and that gives us the negative 9.5. So if we have the analytical derivative, everything we've just done, most of this class, gives us a really nice just copy and paste kind of approach. But often we don't have nice derivatives. This is an example where we do have a derivative. Last class we used the power rule and then the product rule to give us this derivative. So this is the function, and then the derivative of this, it looks like this. So this is our g prime. And then here, this is a little more complicated because we have two, if we're thinking about these as optimization solutions, there are two ways that this function can be 0. One is the maximum and one is the minimum. So if we're setting our derivative equal to 0, that happens to be in two different places. So this is slightly more complicated than the original version because we have to think about the Newton-Raphson behind the scenes and how it finds the solution. So we have fsolve, we plug in dg, the derivative function, and then we're just trying to pick two different starting guesses, which, using our figure, which is a good place to start, using the figure, we're going to try to get close to one or the other. So the first one is 0, so I'm just going to start somewhere below where I think this will be. And then the other is 20, so I'm going to start definitely on the upper end, close to the upper root. So I run this, and then again I get something that looks pretty nice. And as we've talked through, mathematically this must converge in these two-dimensional settings. So we found the first root, and then we found the second root, and then we evaluated both, and that's awfully nice. Nothing radically new here, right? All we're doing is, if we know the derivative function, finding the root really matters, right? It's that finding the root of the derivative gives us the optimized values. In this case, we have two of them, so we have to think a little more carefully about how the Newton-Raphson is working. But beyond that, as we've done in the last notebook, this is all pretty standard. Okay, but part of the problem we're trying to dig ourselves out of is that sometimes we can't take the derivative. Like, sometimes it's too hard for us to do. Sometimes we don't want to do it, which is, sometimes we encounter those kinds of situations. So how do we get ourselves out of this problem, right? That's the fundamental goal of numerical methods, is how do we not have to actually do the solving. So the way we dig ourselves out is by realizing we can just perform Newton-Raphson, but on the derivative. So instead of thinking about the function as the function that we put into the Newton-Raphson, what if we just try to give it the function and then have it internally do a first derivative and then a second derivative? So instead of thinking about the function as what's being input, we think about the derivative function as what's being put into the Newton-Raphson. So we're sort of going up a level of abstraction. So we say, I don't care about this figure. I don't want you to Newton-Raphson on this one. I want to give you this thing, but then you find the numerical derivatives and then perform Newton-Raphson using the numerical derivatives to find Newton-Raphson of this. Does that make sense? So all we're doing is basically just replacing f for f prime in our Newton-Raphson. But there's not a whole lot of extra conceptual challenge here. We're just saying, I don't care about f, I want you to do Newton-Raphson on f prime. Even though I'm not giving you f prime, we can calculate it using numerical methods. Okay, nice. So let's replace f with f prime. Everything in Newton-Raphson looks identical. It's just, now it's f prime and f double prime in the top and bottom. Okay. This is what, lots of gradient-based methods are using. We're going to use scipy optimize.minimize. There's no maximize actually in optimize. So if you're trying to maximize a function, you just take 1 minus the function. You just flip it, and then you'll be minimizing the opposite. Okay, so let me just talk you through what we're doing here. This is not a lot of extra conceptual work. The main idea is that we want to evaluate the derivative and not the function when we construct the Newton-Raphson. And what we're doing with this Newton-Raphson optimize is giving it the function, giving it a guess, giving it tolerance. But in this case, we have to give it some epsilon. So in addition to the Newton-Raphson we used before, we have to give it an epsilon because we're forcing it to take a derivative for us. And like we talked about with numerical derivatives, we have to specify the increment for the derivative. So we have both a tolerance, which tells us how close we want it to be to the optimum, but we also have an epsilon, which is related to the derivative. And these are separate ideas. We need both of them. Any questions about that? So we have both the tolerance when the Newton-Raphson stops, but now because we're trying to root find on the derivative, we need the epsilon for the increment for the derivative itself. So first I'm going to take a first derivative of the function at the guess using the epsilon, and then I also have the second derivative of the function, which we defined last class. And then this is just the Newton-Raphson step. So this is the first derivative over the second derivative, which is the analog to the Newton-Raphson we developed in the last notebook, which was just the function evaluated at our guess divided by the first derivative of the function evaluated at our guess. So this is Newton-Raphson, but on the first derivative. And then this is just making sure we get close to 0. Okay, and if it doesn't, after we go through max steps, then it says it doesn't converge. So I'm going to run this, and then we're going to find our roots. Okay, and the caliber of my jokes is I was thinking about making a joke about the restaurant, talking about root finding. Thank you for being here. So we have the minimum for f, which is 2.5 as we've confirmed before. We did this using root finding with Newton-Raphson, but knowing the analytical derivative. So here we're just confirming that this approach using an approximate derivative gives us the same answer as when we used the analytical derivative with Newton-Raphson. And then here we have the minimum, and then we have the maximum. Okay, any questions here? Hopefully with all this buildup, this is sort of a culmination of a lot of ideas all at the same time. Okay, so like we've sort of seen with the G function, we have two types of optima, the maxima and the minima, and we need to we want some systematic way of checking which one is which. The root finding just tells us where the roots are, but we also want to make sure we're getting we're separating the maxima and minima. So you'll remember from your more theory-heavy portions, when you have curvature that's downward sloping, that tells you that it's a local maxima, and when curvature is upward, then it's a local minima. And we just want to differentiate between these two. So what we can do is we found the solutions. So the maxima and minima up here. So we've found our two roots, G sol 1 and G sol 2. And all I'm going to do is plug them into the second derivative function. So I don't know if I explicitly mentioned this, but I've just carried over the first and second derivative from the first notebook and called them derivative 1 and derivative 2 up at the top. And all we're going to do is actually just find the second derivatives at these roots. So when I run this, I get the first root, and then I get the second derivative. Because it's positive, this tells us it's curved up, which means that's a local minima. And then for the second one, I have a second derivative that's negative, so this tells us it's a local maxima. Okay, not a whole lot of theory here. the reason, what this is doing, the reason it's important is because sometimes we care about, without checking the graph, we would want to just confirm that it's a minima or maxima. We found the roots, we've gone through that whole process, we want to know which is which. And this is just a figure of this, finding the roots. And then, we also care about global. One of the nice things about computers is if you find a bunch of roots, you can just check the values. So like the systematic approach to finding local and then finding global maxima, really the way to do it is just to check the numbers, right? There's, you can't take derivatives of anything to get you nice solutions. You just have to evaluate the functions. So when we zoom out to see a larger picture, you can see some of the problem here. This is a local maxima, but it's not the global maxima. This looks to be the local minima, or it is a local minima, but it appears to be a global minima. If we can confirm this is an asymptote at 0. Okay, so not a whole lot of theoretical solution there. Maybe the last thing we'll do today, I just want to show you this particularly challenging function, wavy. Looks like this. I hope you never encounter this in your daily life. Maybe if you're lifeguarding, you see this on the water, but hopefully you don't encounter a problem that looks like this. What I did here, I just set up so we have, in the figure, I have a bunch of starts. So these are the starting guesses, and then I'm just looping through them using SciPy minimize, which is really equivalent to the fsolve that we've just used on the wavy function. So we start a bunch of different values, and then run an optimizer. And then I'm plotting the results. So this is the result, and then the result evaluated at the function. And then I have this anti-wavy. So this is 1 minus the wavy function. So I'm just defining anti-wavy to be the negative of wavy. For some reason, SciPy optimize doesn't have a maximizer. So to do a maximization, you take 1 minus the function and then minimize that thing, which looks like this. So we're just gonna use the same starts and then run the optimizer over this. Okay, and it looks like this function. And you'll notice a few things. First off, with our starts, we missed one. We missed one of the maximas. We got all the minimas, but we got 2 of the maximas. So confirming with your figure, like a lot of this is just to convince you that you have to be careful, and you have to think carefully about your problem. When we're in this world, the nice solutions are not as nice as they were when we have nicely behaved functions you can take derivatives of. You have to be particularly careful. So this is a hard one because it's so wavy, so you have to be careful. If you were to add more increments, you could probably do better. So yeah, just be careful with these things. And then the last thing, maybe we'll save this for next time. I don't want to start a deeply new topic here in the last 4 minutes of class. But all of these approaches we're taking extend into higher dimensions. So we've really been dealing with 2 dimensions, the x input as one variable, and then the functional output as the second. So we can plot this in 2 dimensions and think intuitively about what Newton-Raphson is doing. But we can use Newton-Raphson on more complicated functions in higher dimensions. So these are the kinds of things we'll turn to next. And we'll extend our notions of root finding and local minima and local maxima into higher dimensions. Are you all familiar with like the Hessian matrix? Okay, so maybe we'll do a bit of theory too, but we'll get there on Monday, bright and early. Should we leave it here? See, if we had taken a 10-minute break, we could introduce this, but I don't want to run over class. So let's take a 10-minute break next time. All right, nice seeing all of you. Hope you're doing well. Job search is hard. Don't let it discourage you. It truly takes a long time.